Okay, so I was just saying that I wanted to talk about some work which I did with one of the long-term visiting students as well as Heisenbag students during the lockdown. It's a work that I never got a chance to talk about. So this is in archive as this preprint 2011.15118, and this is with Nachiket Kavi, who was a student at IIT Kanpur, and he's now a graduate student at Boston University. Okay, so the basic topic I wanted to talk about was how to think about Heisenberg picture for open quantum systems. So that is the thing that I want to talk about. So let me just remind you about some very basic facts. Most of this talk is completely elementary, and it doesn't require anything more than basic quantum mechanics. Okay. So the point here is that in basic quantum mechanics, we learn that one can define quantum systems, one can describe quantum systems in either Schrodinger picture or Heisenberg picture. And the Schrodinger picture is about describing it as an evolution of a state or evolution of a wave function. And Heisenberg picture, which is an earlier way of thinking about quantum mechanics due to Heisenberg, what we think about is we think about evolution of operators, right? Okay, in some operator algebra. Okay, so the statement is that for any system you have an algebra of operators, and then you have one operator at a given time, and that operator evolves with time. Okay, so that is the basic idea. So this problem was motivated by this question on how we should think about this kind of Heisenberg picture for a quantum system which is not a closed quantum system as in the textbooks, but it's a system which is then in contact with some outside quantum system, which I will call as bath. Okay, the question is that how do you think about Heisenberg picture for this system? What I mean is that how do you associate an algebra of operators or for this system which then evolve? Okay, now this is a very basic question, but it kind of is. If you start thinking about it, you realize that it's a very confusing question. The statement, the reason is as follows: that let's say you start with an operator. Okay, so the statement here is that in this case you have a tensor product Hilbert space. Okay, so the full Hilbert space, okay, is given by a Hilbert space of the system, which I will denote by H naught, and a Hilbert space of the bath, the tensor product of that. Okay, and what you can do is that you can start with some operator. Okay, let's say some Heisenberg operator. Now, of course, there's a Heisenberg picture for the full thing. Okay, that's a standard quantum mechanics. Now you can start with some operator. Okay, let's say some operator which looks like some O times identity. Okay, where the O acts on H naught and the identity acts on HB. Okay, and now so this is at t equal to 0. This is a Heisenberg operator of the full system. Now you evolve it. Okay, if you do a Heisenberg evolution, in general, what happens is that this becomes some very complicated operator acting on H naught HB. Okay, so there's no sense in which you can associate an operator, which just acts on H naught. Okay, so this is a general statement, and that's one way of saying that these things get entangled. Okay, and so on. So in general, you get some mixed operator. Okay, and there's no sense in which you can kind of give an operator which just acts on the system H naught and not on the full thing. Okay, so the question is that so you have this. So if you really think about it, this is just to kind of make the statement clear and why this is so confusing. It says that if I am coupled to the environment, as all of us are. Okay, the position operator of me, okay, for example, is not really an operator acting on my Hilbert space. Okay, so that is not in Heisenberg picture. Okay, and that's not often appreciated. So which means that any system which is coupled to some kind of an environment. Okay, its operators might not even be an operator acting on its own Hilbert space. It's usually an operator acting on some other thing. Okay, it could even be an operator which just acts as identity on H0 and acts as HB, and it can evolve into that. Okay, so that is something that that can happen. So then, which means that like how do you think about Heisenberg picture in this kind of thing? Okay, so we gave two like kind of answers to this question, and I'll kind of summarize these answers. So one way to think about like Heisenberg picture is to kind of is to actually not ask for a single operator, okay, but you can ask for like a multiplicity of operators. So let's say like I have a basis, okay, which is call it as alpha, okay. Let's say HB is really spanned by some basis vectors which I'll denote by alpha, okay, alpha, beta, and so on and so forth by Greek letters. Okay, what I can do is that I can take in general this O of t, okay, some Heisenberg operator for the full system, and I can project it, okay, with respect to alpha beta. So I can define, okay, O alpha beta of t, okay, which is as just a partial trace, okay, over the path of something where you have identity on the H0, and then you have something like beta alpha, okay, this is in HB, and then you have O of t. Okay, so you can, this is my definition. Okay, so this defines if the dimension of HB is n. Okay, so this defines n square number of operators. Okay, so the statement is that like if you don't want to lose any information, okay, one thing you can do is that you can take like this Heisenberg operator and kind of project it, okay, and get like an n square number of operators. For example, in this problem, I can define n square number of position operators if I'm coupled to some environment, some bath of dimension n, Hilbert space dimension n. Then I can define n square number of position operators for me, okay, which acts on my own Hilbert space. Okay, and you can convince yourself that like this doesn't lose any information. For example, I can write down the Heisenberg evolution, okay, equation for such an operator. These operators as follows. You can just take like the usual Heisenberg evolution, and then I can just write it as I over h bar, some h alpha gamma, okay, and O gamma beta minus h O alpha gamma h gamma beta. Okay. So where these h's are again image operators which are defined. So this is what I call as image operators. Okay. So I can also take the whole Hamiltonian, okay, of the combined system, and then this is an exact statement. That is, like I can define a set of operators. So remember, this is an operator on H0. Okay. After you trace over the bar. Okay. So I can just start with n square number of operators, okay, acting on H0, and I can kind of Heisenberg evolve them, okay, if by also having n square copies of the Hamiltonian, okay, and this is a basic linear algebra to kind of check that that this is actually an exact statement, okay, that you can always do this whenever you have a tensor product. You can always like take the Heisenberg evolution in the full system and project it to a Heisenberg evolution of these image operators. This is some coupled evolution. Here gamma is summed over. Okay, so I'll just using Einstein summation convention here, gamma is summed over. So the statement is that like what you have is a kind of n square number of operators, n square copies of every system observable, which are all coupled and they evolve in a certain way. Okay. So this is an exact statement, and this is one way to answer the question, what a Heisenberg picture for an open quantum system looks like. Okay. Mathematically, this is a very basic statement, though it's very, somewhat confusing. Okay. If you start thinking about what this physically means, it means that, like if I'm coupled to the universe, okay, I have as many positions, okay, as there are observables in the universe. Okay, right? So that's what this says. But this is just linear algebra. Okay, so that's a statement. So the question is that so how is it? You might ask, okay, that I don't see myself having so many positions. okay, and position operators. So of course, the point here is that, so one can kind of understand that by asking, how the system, all these operators, whether they can be reduced to a single operator. For example, one thing you can do, okay, one thing you might naively do, is to define, let's say, some OS of t, okay, which is just, rather than doing this, okay, you just take O of t, and then you multiply it with some bar density matrix, okay. So if the bar has a density matrix, you can kind of reduce it, okay. Now, you can ask, so one other way to think about system is that whether I can just write down an evolution equation just in terms of this OS of t, okay, which is just a system. You can call it as a reduced Heisenbag density operator. This is what we would call as the position operator. For example, if you want to, for example, calculate the expectation value of position, what will you do is that you will kind of take this guy and trace it with rho naught, sometimes a OS of t, okay, would then give you the expectation value of O of t, calculated in the this thing if your density matrices are actually factorized, okay. The point here is that, so what we did show is that, you can kind of, under certain assumptions, you can actually reduce these image operators, okay, these n square image operators to kind of, to OS of t, okay. And what you can do is that, so basically the basic idea, just 1 minute. Basic idea is to kind of, think about the Hamiltonian as also a sum of, a Hamiltonian of this and this with some interaction. And what you can do is that you can do in arbitrary order in perturbation theory, okay. You can solve for this O alpha beta of t, okay. So in terms of, can be solved in terms of this OS of t, okay. But the price you pay, so is that, when you solve it, okay, that depends a lot on the bar density matrix, okay, in a very, rho b dependent way, okay. So the statement is that, you can indeed define a position, for, a system. Let's say you can define a position operator for me, but then that position operator, if you have to define it and give a self-consistent, description of the position operator, what you have to do is that you have to kind of define it in a very bar dependent way, okay. So there are various expressions and so on and so forth, which since I've run out of time, I won't do that, okay. Anyway, they're all there in this treatment. You guys can look at it. Okay. So let me just stop here, okay, and I'll take any questions.
Yeah. So any questions?
Loga, this may be naive, but in non-equilibrium StatMech, there's the Maurice-Wanzig formulation that you do for projection operators, yes, or in condensed matter, Caldera-Leggett. This is very similar to that if you write the equation for OS.
Yeah, so usually it is done in Schrodinger picture, okay. The question is that, you can try to understand how would it look like in the Heisenberg picture. I didn't have time to say why, you might want to look at Heisenberg picture. Basically, because Heisenberg picture has its advantages. You don't want to keep track of the full density matrix and so on. You just want to calculate some correlation functions. Heisenberg picture is better, for that. Okay, so that was one of our motivation for looking at Heisenberg picture. Okay, yeah. So the point is to kind of, I think you can reformulate many of these, the projection operator formalism, for example. Okay, in terms of these guys. Yeah. Yeah, yeah, okay.
I have a question. Sorry, sorry, go ahead.
Yeah.
Yeah, I was going to ask the same question. In the other formalisms, you encounter a memory, which then you have to compute from the properties of the bath and so on. Here you have this proliferation of operators. So
yeah, I think this proliferation of operators indeed, is a very exact way of keeping track of memory. Okay, in the sense that this statement I have written here is actually an exact state. It is linear algebra. Okay, you might not want to keep track of all these operators as we showed, but the point is that this is a very independent of the bath state. independent of whether bath has memory or not, and so on. So this statement is the exact statement of how you should think about Heisenberg picture for open quantum systems.
Thanks.
Hi. Actually, I didn't get many things. Why are we defining this quotient operator? Like, how is it helping in this bath picture?
Why are we defining
This quotient operator that
this
you
is
have
O
to
alpha
do-
beta, or
the OS T.
so
you're
OS of
taking-
T, in principle, this is completely fine. Okay, you don't have to do anything. It's just that it's a bit, like both. It's exact, but it's too profligate. It's just there's too many operators to keep track of. Okay, but if you can do it, it is exact. Okay, and it's also kind of bit non-intuitive. Okay, to keep track of n square number of observables for every system observable. Okay, but so one of the things that this is to kind of make contact with both standard intuition and as well as standard description of open quantum systems. Okay, where you could kind of reduce these operators to a single operator. So that's what we are arguing. Okay, but that also has a cost. Okay, but you have to do it in some very state dependent way. Okay, so either you can have a state independent description. You don't have to ever mention rho b. Okay, but then you have to keep track of all the operators. But or you can very crucially use the state of the bath. Okay. In which case you can try to reduce it to a single operator, okay, but in a more complicated way. Yeah.
I have one more question. So if I want to do some measurement on the bath, what I can do is actually I can evolve the entire system with this system plus bath, and I can do a projective measurement on the bath, which will actually account for some measurement on the system. So how does this evolution of this just the system will help me? Like how is this picture helping me instead of like avoiding this measurement idea? And
yeah, so so this O alpha beta are all like operators on H naught. Okay, and they're supposed to allow you to calculate correlation functions of the system. Okay, now if you want to do a measurement on the bath, okay. First of all, you might want to keep track of the bath, okay, right? Because I don't have, once I go to this, all these are operators on only the system, okay? I don't have any, like bath operators, okay? But, like what you're saying about, like some bath measurements being equivalent to system measurements, okay? I haven't thought about it, but maybe there is a way of thinking about it in terms of these image operators where, like some bath measurement can then be transported into these image operators and measuring something in the system. But yeah, I have to think about how that exactly the mapping works. But eventually the point of this n square operators keeping track of all the entanglement between the system and the bath if you want. Okay, and hence in principle it should allow you to do all the things that you want to do. All the things you measure in the system, anything which is equivalent to some measurement in the system, you can reduce it, some correlation function of the system, you can reduce it to this image operator.
So, okay, we can
Thank
take
you.
one more question.
Hello?
I think there was a question online.
Yeah.
Yeah, we can take that.
Hi, Loga, can you hear me?
Yes, I can hear you.
Yeah, so my question is there any advantage of this method of doing this evolution numerically? Let's say if I have very highly complicated interacting system, will this method be more advantageous than other existing methods?
I think there are some advantages, like to this method. The main advantage is that, so there's a particular way of approaching open systems, which is called as a hierarchy equations method, which is basically, rather than asking, what are the density matrix and its evolution, as we usually do, you can ask, I just want some correlation functions. I just want some time dependence of some correlation functions, and I don't want to keep track of all the density matrix and so on. What you can do is that you can write down that correlation functions in terms of these image operators, and you can write down some equations obeyed by the correlation functions, which are derived from this Heisenberg equation, and you can just solve that. Okay, so often that is more easier to solve than to solve for the full density matrix in which many complicated things are going on. Okay, sometimes you're just interested in correlation functions of certain observables. Okay, and you just want to write down equations for those certain observables. And one of the things is that this formalism allows you to write down those equations, and then you can numerically solve them. Okay, just for those observables, rather than trying to solve for the full density matrix.
Okay. And another question. This thing I can think of as your system as a subsystem of a bigger system,
Yes.
right? And then can this formalism be used or extended to derive an hydrodynamics for the subsystem? Considering it as a coarse graining and use this because you are considering only the observables, not the full density matrix.
Yeah, that was one of our motivations, but yeah, we haven't come around to doing that. Yes, yeah, exactly. The hydrodynamics, for example, in hydrodynamics, again, we are just interested in energy momentum correlations. We're not interested in the full density matrix and so on. Okay, so yes, so ideally we would just want to write down some equations for this energy momentum tensor and its evolutions, and just repackage that into hydrodynamics, and just forget about the full density matrix, which is usually some complicated mess. Right. Okay. Yeah. So that's one of our motivations, but we haven't really come to applying this to a case like that. But indeed.
Okay. Thank you.
Okay, so let's thank the speaker again.